This screencast is going to focus on measuring concentration, what it means, and also how to calculate it. And so when chemists talk about concentration, it's talking about the amount of particles that are present in a solution. And so like we've said before, solutions don't have to be liquids, but these mixtures typically do focus on the liquids and how we express them. So one of these is actually one you've seen before in the laboratory. You may not have understood what it meant, but you've seen when we've done different labs, maybe we might be using 1 molar HCl versus 6 molar HCl. And so as a teacher, I'm certainly more concerned when we're using 6 molar hydrochloric acid in the lab, because what that really means is there's more stuff in the same amount of volume. So if we talk about a 6 molar solution versus a 1 molar solution, we know the solution has 2 parts, and so there's hydrochloric acid and then there's also water. And so in a 6 molar solution, you're going to have a lot more moles of HCl, which is really the hazardous stuff, versus the water. And in a 1 molar solution, you're only going to have 1 mole of solute of the HCl in the same volume of solution. So a quick visual for this, if you look at what they're doing here, this is obviously a colored solution of some sort. Probably a cobalt, because cobalt solutions tend to have that color to them. And not all solutions have color, obviously. But this is a nice visual kind of what concentration means. So when we say that something is dilute, that means that there's not a lot of solute in that particular volume of solution. And if you notice, as we increase in concentration, we would say that this one on the right is the most concentrated because it's the darkest solution. So that's telling you the thing that's causing the color, which happens to be the solute in this case, that there's a lot of it in that same volume of water. So that's kind of a visual. You can also think of your Kool-Aid, right? If you think about the amount of sugar that you're trying to force into Kool-Aid, if you put a lot of sugar into the Kool-Aid, we would say that that's a concentrated solution. And so the same idea. So the 3 that we're going to learn about today are percent by volume, which is more of a commercial application, molarity, which is what chemists use the most, and then something called molality. And honestly, molality is more of an industrial term, and we use it in one particular section of what we do this year in chemistry, which is why we need to know about it. So we'll start with kind of, I think, the most accessible, talking about percent concentration by volume. So this is the volume to volume ratio between the solute and the solution. And there's a little reminder here to remember that solution consists of 2 things, both the solute and the solvent. So if they give these to you separately, then you would have to add them to get that volume of solution. So we'll go through a couple of examples and see how they work out. So in example 1, they say that 5 milliliters of vinegar are dissolved in 50 milliliters of water. So I think it helps to kind of label what's what. So the vinegar would be the solute, and the water would be the solvent, and then the diluted vinegar solution would be your whole solution. So they're saying, what is the volume to volume concentration? So if I do percent by volume, by identifying the solute, we know that that goes in the numerator. So we take our 5 milliliters and put it on top. And then in the bottom, we need solution. And so we said the solution consists of both of these. So I've got to add my solute to my solvent. Now, just a reminder on significant figures in addition, because it is different than multiplication. When we go to add these 2 together, I'm not going to cut this to 2 sig figs because of the 5.0. I'm going to keep that decimal place, right? And so I end up with 5 milliliters over 55.0 milliliters. I multiply it by 100 to turn it into a percent, and I come out with 9.1%. So I am limited to 2 significant figures because of that numerator being 5.0. All right, in example 2, it's a little bit different because they tell you it's a photographic stop bath, so the way they used to develop photos. It contains 140 milliliters of pure acetic acid and 500 milliliters, and watch that term right there, it's solution. So they're telling you that the solution total is 500 and that 140 of it is your solute. So in this example, we are not going to add the 2 numbers together. So you just have to watch how they give it to you and watch the wording really carefully. So in the numerator, I'm going to put my 140 milliliters, and the denominator, my 500 milliliters, and multiply it by 100, and I end up with 28.00%. So that is percent concentration by volume. if you go to the drugstore and you purchase, alcohol, like isopropyl alcohol, rubbing alcohol, or hydrogen peroxide, a lot of times you'll see those percent expressions. And so now you know that that's the percent of stuff, and then the rest is just water, assuming it's an aqueous solution. All right, so molarity is the most common way that chemists are going to express concentration. So if you're just given a problem and it says, hey, what's the concentration of blank? They most likely 99% of the time mean what is the molarity. So obviously these can be pretty straightforward if they were to give you moles of solute and the liter of solution, right? This is honors chemistry though, so they're not going to be as straightforward. And we'll probably have to do some work to get things into moles and get things into liters. So you may want to make a note that 1 milliliter is equal to 10 to the negative 3 liters. Or if you like working with it, there's 1,000 milliliters in 1 liter. This is a handy conversion. So in example 3, it says, what's the molarity of a solution that's created by dissolving 3 grams of silver nitrate in enough water to make 100 milliliters of solution? So neither of those units are in units that we need as far as moles and liters. So our solute is the AgNO3. So I'm going to take my 3 grams of AgNO3, and since it's the solute, I need to get it into moles. So grams are given, grams are going to go down, and I figure out the molar mass for AgNO3, which is 169.9 grams. So that is equal to 0.0177 moles. So I've got one of the units that I need. I've got my moles of solute. And then my 100 milliliters of solution, I need to get that into liters. So I'm basically moving the decimal, right, 3 places to the left, and I get 0.100 liters. So now I've got my liters that I need. And so all molarity is the ratio between the moles of solute and the liters of solution. So in the numerator, I'm going to put in the 0.0177. In the denominator, the 0.1, and my molarity then comes out to 0.177, and we can say big M, or we can say moles/liters, whichever one you like. I do think in the beginning writing moles/liters kind of helps you learn the formula, but big M is fine. You cannot use little m, because little m is going to be down here for molality. All right, our second example, still asking for the molarity. The copper 2 sulfate, we've got 80 grams of the solid, so that's our solute. And we're making 1,000 grams of solution, and then notice they've given you the density of the solution. So we can't use grams in a molarity formula. If it's the solution, it needs to be in liters. So we think about, well, how can I get this 1,000 grams if I know the density? And if you remember, density is just mass over volume. So if they've given me the density is 1.03 grams per milliliter, and they've told me that you have 1,000 grams, then we can basically solve for x or solve for the volume. And so when we do that, we multiply both sides by x and then divide by 1.03. Our x, or our volume of solution, comes out to be 980 milliliters, because that was the given in the ratio of the density. And so I'm going to have to convert that to liters. And so if I move my decimal 3 places to the left, I get 0.980, being careful not to lose that significant figure on the end. So that's how many liters I have. So I've got the right unit there. Now I've got to get the 80 grams of the copper 2 sulfate into moles. So the CuSO4, and technically this is probably a hydrate, so it's probably copper sulfate pentahydrate. They didn't give us that, so we will just pretend that it's regular old copper sulfate. So getting the molar mass for that using the periodic table, we get a molar mass of 159.6. So 80 over 159.6 gives us 0.501 moles. So I'll switch colors just because that's getting a little messy. So when we go to solve for a molarity, I've got my moles now, I've got my volume, and so I'm going to do the ratio between the moles and the volume. So 0.501 divided by 0.980, and my concentration comes out to 0.511 big M. Just a note, when you see brackets around something, so if you saw something like this, brackets and then CuSO4, the brackets actually stand for concentration. So it's a shorthand, it's a way to say, hey, the concentration of copper sulfate. And so if you see brackets, that's what they were looking for. And again, 99% of the time, they are looking for molarity, not the others. All right, so the last one is molality. And so notice it gets the little m as its abbreviation. And so molality, like I said, is typically an industrial term. When you're dealing with kilograms of solvent, so kilograms of solvent probably makes you think, well, that's probably not in liquid form. Sometimes it is, and in a factory, it's just easier to measure the mass of something than it would be to like have this ginormous, graduated cylinder or something that's trying to measure volume. So, like I said, it will come up when we do something called colligative properties, and so that's why we need to be able to calculate molality truly just for that one simple application. So if we look kind of at how it's different, moles of solute is still the same, it's still in the numerator, but what changes is it's kilogram, and the tricky part is it's just kilogram of solvent. So whereas percent by volume and molarity was solution in the denominator and you had to add, with molality it is only the solvent. And again, because of that industrial kind of application, they're measuring these two things separately and they're mixing them in some big vat, to get a reaction. And so it's very typical to measure the solute and the solvent separately. So just something to be aware of so that when you're learning these formulas, you calculate it correctly. All right, so number 5, very straightforward. They're giving you 3 moles of sodium chloride, and it's dissolved in 1.5 kilograms of water. And so the molality is the moles. So the 3.0 moles of NaCl is your solute over the 1.5 kilograms. And so we get 2.0, and we can say a little m, or you're welcome to say moles/kilograms. All right, example 6. What is the molality of a solution in which 25 grams of calcium chloride, so there's our solute, is dissolved in 2.0 kilograms of water? So that's our solvent. So when we go to check our units, I need moles of solute. I'm currently in grams, so that one's going to have to go to moles. And then I need kilograms of solvent, which I've already got. And so I'll do my 25 grams of CaCl2. Don't forget to still balance your charges on your ionic compounds. And so CaCl2 has a mass of 111.1. So we end up with just 2 significant figures in our answer, so 0.23 moles. So now I've got my moles of solute. I've got my kilograms of solvent. And so to calculate molality, on top, we're going to do 0.23 moles, and on the bottom, 2.0 kilograms. I divide, and I get 0.12, and again, little m, or you can say moles/kilograms. All right, so those are the 3 different ways we'll calculate concentration. So if you flip to the back, you've got some practice there. You've got percent concentration by volume first, some molarity practice, and then some molality practice. See how those go? We'll go over them, and we can talk more about it tomorrow.